Okay, so I'm going to go ahead and show how this approximation method works. So if we have an acid, let's just call it HA. You got to call it HB also. And we have it in a solution. We put it in water. That gives us, and he's got the H, so he's going to give it over A minus. A lot of people do this A for standing for anion and H3O plus. Now, because I made H3O plus, that means it's a Ka. And so A minus times H3O plus over HA. All right, so let's say we look this up and we find out that the Ka is 1.5 times 10 to the minus 9th. And let's also say that we know initially I had 0.1 molar of HA. Okay, so when I go to fill this in, that's minus x. Remember, the water doesn't matter. That's 0, 0, plus x, and so I get x and x. So I've got an x for this and an x for this. So I'm going to just rewrite it as x squared, x times x, over, and then my HA value is 0.1 minus x. And then 1.5 times 10 to the minus 9. Now I know you can pull out your math app and you can plug this in and you can solve the quadratic and you can get to the answer. So imagine that you had to do it the way I had to do it, where in the last chapter you actually were solving quadratic equations. And when you get to this point and someone says, hey, you can make an assumption and make the math way easier, you're like super excited about that. So the assumption has to do with this, because if you didn't have that x in there, it'd be really easy to solve it. So if your K value divided by your initial value, it times 100%, is less than 5, then this will work. If it's not, you have to do the quadratic. So here's our K value, 1.5 times 10 to the minus 9th over 0.1, and then times 100%. And I don't know if you can already see it, but I'll throw it in the calculator. 1.5 e to the minus 9th divided by 0.1 times 100 gives us definitely way less than 5%, right? 1.5 times 10 to the minus 6%. Okay, so the assumption method should definitely work. And as a little note, like the smaller the Ka, really the more and more likely that this is going to be able to work. So what that means, excuse me. So what that means, I don't have time to re-record, is that I can say that x never existed. I got that a little too crazy there. So I can say that that x and that minus I never existed. Now you can see where the math is really easy. So if you take that and you multiply it up, then I just have to take the square root of 0.1 times 1.5 times 10 to the minus 9. So that's fairly easy to put in the calculator. And I actually think it's easier than open up the app and trying to type in the entire thing into an app. So 0.1 times 1.5 e to the 0.1. And I could go ahead and do square root actually right now. Second square root, parentheses, 0.1 times 1.5 e to the minus 9th, parentheses. So that gives me that my x is 0.0000012. Let me just 1, 2, 3, 4, 5. Yep, that's right. All right. So what are we really saying when we did this? So this is the answer I got for x. And let's just double check, make sure that that really is true. So if I got this answer for x, what I need to have happen is that regardless of what x is, or whatever I solve for, it needs to be negligible or not matter compared to that 0.1. So I basically need to get 0.1 at the end. 0, 0, 0, 0, 1, 2. So I'm going to open this calculator at 0.1 minus and answers what I just had in there. So I get 0.099987775, blah, blah, blah. All right, so if I want an answer that has 1 sig fig, I'll round that up. If I want to answer with 2 sig figs, it still rounds all the way up. 3, 4, 5, 6, 7, I'm still going to have an answer that rounds all the way up to 1, 0, 0, 0. You see what I'm saying? This is going to round up. This is that. So it was a fair assumption to say that my x did not matter at all and it wasn't going to change the problem. That's the assumption method. That's how you make your math a lot easier. It's going to work most of the time. again, here's your little key point to know if it's going to work. And if it doesn't work, then you're going to have to put it in app and solve for the quadratic. Or you can solve for the quadratic on your own.